Hello, everybody. Good afternoon. Welcome to lecture. Today we're going to continue our discussion of alkenes, and elimination reactions is really the focus of this chapter. Alkyl halides reacting with a base, where the base deprotonates next to the leaving group, and you get a new carbon-carbon double bond. That's an alkene. So to start things off, we're going to talk more about alkenes. The products of elimination reactions, because it's really important to understand those to appreciate how this elimination process works. We talked about a bunch of this stuff last time, but we're going to talk about more of it today. And then when we get a full discussion of alkene stability, we'll talk about the survey question for the day, because that's pretty much what the survey question is all about, is sorting some alkenes based on stability. We talked about that last time in a kind of a way that wasn't like it didn't have its own section, but today we're going to talk about it really specifically, and then we'll look at it again through the survey question. So first thing I want to talk about with alkene structure is, what they look like. So an alkene has a carbon-carbon double bond, and that's the key functional group in a molecule called an alkene. The alkene, each carbon of the carbon-carbon double bond is sp2 hybridized, which means it's got 3 hybrid orbitals, sp2 orbitals, and it's got an unhybridized p orbital as well. And so we'll look at that in this picture that I'm going to show you on the right. But first of all, let's look at this picture. This is what it looks like when you look at it either from the top or the bottom face. Alkenes, since they have sp2 hybridized atoms, they're trigonoplanar, and you can lay them on a desk or draw them on a piece of paper as a flat molecule like this. And that's usually the best way to draw them. So when you're doing alkene structures on your homework in ALEX or on an exam or something like that, it's almost always best to draw them as flat. So draw them in the top or bottom view so you can clearly see the bond angles around them. sp2 hybridized atoms have 120-degree bond angles. And so what I'm saying here is about 120 because the 3 electron groups on that carbon aren't exactly the same. The electron groups have different repulsions, and so it's not going to be a perfect 120-degree bond angle all the time, but it's going to be very close. So that's one of the things to know about that. And then if you take this flat molecule and you turn it on its side, you can see some other aspects of alkene structure that are interesting. And so that's what I've shown over here. This is the side view with some molecular orbitals showing. So each carbon of the alkene, there's one of them and there's the other one, is sp2 hybridized. So it's got those 3 hybrid orbitals, sp2 hybrid orbitals. 2 of the sp2 hybrid orbitals are going to make bonds to other species. So this dash and that wedge are bonds to something else that they're going to be making, some other atom that they're going to be making using the sp2 hybrid orbital. And then the third sp2 hybrid orbital is one that it's sharing with the adjacent carbon. So each of these 2 carbons have an sp2 hybrid orbital that overlaps, and there's a pair of electrons that are shared in that molecular orbital. And that's what the sigma bond, that's a sigma bond. So sigma bonds, just as a refresher, are electrons shared directly between 2 atoms through overlapping orbitals, and in this case it's sp2 orbitals. And those sigma bonds are strong because it's really efficient sharing. Directly between the 2 nuclei is the best way to share electrons. But there's only room for 2 electrons in that space, in that molecular orbital. So there's got to be other sharing, because a double bond has got 2 shared pairs, 4 electrons total. The second pair of electrons goes into the pi bond that forms when the p orbitals overlap. So this is one p orbital. That's another p orbital. They have 2 lobes. They have an upper lobe and a bottom lobe. And those lobes, when they overlap, they form half a pi bond. So up here, the overlap between the upper lobes is 1/2 of a pi bond, and the overlap between the lower 2 p's is another 1/2 of a pi bond. And there's 2 electrons that are shared in that overlapping space. But since that space isn't like the best, most efficient way to share, like sharing electrons kind of above and below the plane between them isn't really the most efficient sharing, the pi bonds are weaker. So when we see alkenes reacting, and we're going to see that in chapter 10, we're going to see the pi bond is the place where they break. And that's the weak link in an alkene. So anyway, that's a picture of alkene. What else can I tell you about alkenes? The other important thing is classification and stability. So we talked a bit about this last time, but it's a good thing to go over again. So we're going to talk about next here alkene classification and stability. So I'm going to show you structures of a lot of different alkenes and how to classify them, and then how to rank them in terms of stability. And that's important because that determines whether or not they're going to be a major or minor product in elimination. So the first alkene that I'll show you is just, I guess, the simplest one. That's ethylene. This is a molecule that has no carbon groups attached to the carbons of the double bond. And there's only one way to make a molecule like this. It's the only structure of ethylene, and it's actually a really important molecule industrially. There's a lot of plastics that get made out of this. Polyethylene is a really important plastic that goes into milk jugs and into things like shampoo bottles and all sorts of different consumer plastics that you use a lot. And it's made from this molecule. So industrially, that's the most important organic molecule. It gets produced in like just thousands of tons a year. Oh, okay. And then if you look at what happens when you start substituting the carbon-carbon double bond with carbon groups. So like say, for example, I take ethylene and I replace one of the H's with a carbon group like maybe this one, where R equals carbon group. This is called a monosubstituted. Alkene. Then if you put another carbon group on, you can do that actually 3 different ways. So when you put a second carbon group on a double bond, there's several different ways to do it. One way to do it is to put the 2 groups on the same side of the double bond if you imagine the double bond being sliced in half lengthwise. So this is going to be a cis molecule because it's got the groups on the same side of that line, and disubstituted. So this is a cis disubstituted alkene. There are other ways you could do the substituents. You could arrange them such that instead of being on the same side of the alkene, they're on opposite sides of the alkene, but substituted onto the same carbon. So here, they're not both on the same side of the line. It's not a cis alkene. This one is called a geminal alkene. Disubstituted. Geminal comes from Gemini, which is twins, basically. So you can think of these 2 groups as being kind of like twins. They don't have to be the same, but there's 2 substituents, and I guess that's where that derives from. Then the other way to do a disubstituted alkene is to have the 2 groups on opposite or different carbons, but have them on opposite sides of the blue line that I'm drawing here. So this is trans disubstituted. Alkene. So these are all the different ways to do disubstituted. And then, if you think about it, moving a little bit further along, if you put a 3rd group on, you'd get into a trisubstituted alkene, which draw over here. Trisubstituted alkene. And then finally, the most highly substituted version of an alkene is one where you put carbon groups everywhere. Every position on the two carbons that form the alkene, the carbon-carbon double bond, and that would be a tetrasubstituted. And so that's the big collection of alkenes that you'll run into. The thing that's kind of nice is that the way I've drawn them here is in order of stability. So this would be the most stable. Way down here at ethylene, this is the least stable. And they increase as you go through this list from left to right. So let's unpack that a little bit and develop some rules that we can think about this with. So the first biggest kind of rule is that substitution really affects stability a lot. If you look at the list, the more substitution a double bond has, the more stable it is. The least stable alkene was ethylene. It has two carbons that have no carbon groups. When you go to monosubstituted, you have one carbon group. It's a little better. When you go to disubstituted, you have two carbon groups. It's a little better yet. And there's three different versions of this, and I'll talk about why they're ordered the way they are this way. But disubstituted is more stable than monosubstituted. And then you go to trisubstituted, and it's even more stable. And you go to tetrasubstituted, and it's the most stable. And the reason is because double bonds are affected by the R groups. The R group donates a bit of electron density. So I'll put this up here as a like a text line. More substituted alkenes are more stable. Due to each R group donating some electron density into the CC bond, and that helps to strengthen it, or stabilize it a bit. So if you've got four of these carbon groups, each one is pushing some electron density in. That's going to be a much more electron-rich carbon-carbon double bond than if you had fewer. So over here, we've only got three carbon groups pushing in. The little arrows that I'm drawing on these lines are meant to indicate the direction that the donation is in. So the R groups are donating electron density to the carbons of the pi bond, or that are making the pi bond. And then with disubstituted, you have two of these groups. They're just arranged in different locations. And with monosubstituted, you only have one. And with ethylene, you don't have any. So that's the first rule about stability, is more substituted means more stable. And then another rule that's important to note is that steric strain makes a difference as well. So I'll put this in as a statement. So I'll say for alkenes with the same degree of substitution, the alkene with less steric strain is more stable. And I have these disubstituted alkenes as a good example of how to interpret this. So if you think about these R groups as being big, so they're larger than hydrogen, so we have these R groups. In the cis, they're close to each other and they're getting in each other's way. So that's steric strain, pretty big, maximal steric strain. When you put them on the same carbon, there's steric strain, but it's not quite as bad. And the best way I can think of to explain this is just ask you to build a model. Because carbon-carbon double bonds are short, these groups are actually kind of close together. And so geminal is a little better than cis, but it's still got R groups that are somewhat close. Trans is really the best though, because it puts the larger R groups as far apart as possible. So trans is the best kind of disubstituted double bond, and you can apply this logic to other alkene mixtures that you're looking at to try to assess which one is going to be the most stable, or between two alkenes, which one is more stable or less stable. And that's what this survey question was about. It was a bit of a stretch to get people to try to answer it, because you aren't, after this discussion, the class would have much easier time with it. But what I gave you last time was enough to sort of get you thinking about it, but maybe not comfortable enough to answer the survey question. But let's take a look at this and see what the survey question is asking, and then try to interpret it for you so you can apply these concepts and hopefully get it to make sense. Rank the following alkenes in order of stability. So first thing to do is to determine the substitution level. So hopefully this is a skill you can all get good at, is look at the carbons of the double bond and ask yourself how many carbon groups are attached. With skeletal structures, it's actually pretty easy, because you just look at how many things are coming off this carbon. There's one over here, and this carbon has two, so this is a tri-substituted alkene. Up here, number one, there's one group coming off that carbon, one group coming off that carbon, so that's a disubstituted. 2 is another tri-substituted. That carbon has two groups, that carbon has one, and 4 is a disubstituted. Each carbon of the double bond has one carbon group. So we've got tri-substituted, which are more stable, and disubstituted, which are less stable. So the two most stable ought to be 2 and 3, and almost the vast majority of the class got one of these two answers, which is basically putting them in the right classification. So let's talk though about why 3 is better than 2. They're both tri-substituted, but which one has less steric strain? Which one has more steric strain? If you look at 3, what you can see with 3 is we've got an ethyl group and a methyl group that are cis to one another. Those are the interactions you want to watch, because those are the really big strain-inducing interactions. So it's like when we were looking at alkane conformations and we had two big groups eclipsing. That was bad. In alkene stability, what we're looking for is a similar thing. We're seeing two large groups getting close to each other, and that's what they are like in the cis. So here it's an ethyl and a methyl. Those are cis. That generates steric strain. But then if we look at structure 2, we've got an ethyl and an ethyl. So two bigger groups, like ethyl is bigger than methyl. So up here, we've got a really large group and a really large group together, whereas here, it's a really large group and a somewhat smaller group. So this one generates more steric strain. This one is less stable. So the most stable one would be 3, because it's got the highest substitution and the less steric strain. So 3 and 2 are the first two. Then we have to look at the disubstituteds and answer those. So between 1 and 4, 1 has got the trans alkene, which is less steric strain, and 4 has the cis configuration, which is got a lot more steric strain and is less stable. So the ordering is 3, 2, 1, 4. 3, 2, 1, 4 is answer D, and a lot of people got it. Actually, it was the most popular answer. So I'm going to go over here to the statistics and just show what the answer distribution was. Hold on a sec. Well, yeah, there it is. Okay, so D was the most popular answer. That was good. Second most popular answer was E, which is the other one that sort of makes sense, but just except not with the cis-trans disubstituted. So overall, I think people are getting it. But with today's discussion of a little bit more of these details, I think you'll be able to, really answer questions like this confidently and correctly every time. So, excellent. Any questions on the survey? Or about alkene stability classification? All right. Well, then we can start talking about specific mechanisms for substitution. Monday's lecture was all about general things with elimination, which are like rules that can apply to pretty much any mechanism. Today we're going to look at the specific mechanisms that are active in this chapter. And so we'll start with the first one, which is, let's see, where is my, there it is, favorite eraser. It's amazing. There really is a difference. The other one streaks. This one is like, erases like a dream. Okay, so there are two mechanisms that we're going to talk about for elimination. And they are called E2. This stands for elimination. That's the big capital E is for that. Second order, or bimolecular. That means that two species come together in the rate determining step. We'll talk about that when we talk about that specific mechanism. And what I'll tell you is this is related to the SN2 mechanism. So substitution mechanisms and elimination mechanisms aren't the same, but they do share some characteristics that are pretty striking. So we're going to look at some of those and compare and contrast. E1 is the other mechanism that we're going to look at. This stands for elimination. First order, or unimolecular. And this is where there's only one species that's present in the rate determining step in the rate law. And this one's related to SN1. Very closely related, actually. They share the first step. So they're going to be very tightly connected. So we'll go through them one at a time, just like we did with substitution. The first one we'll look at is E2. Just like we looked at SN2 as our first substitution mechanism, we'll look at E2 as the first elimination mechanism. So here's an example of an E2 reaction. So E2 mechanism. So I'll use a specific example to illustrate the mechanism. I'm going to show elimination in a molecule, tert-butyl chloride. So tert-butyl chloride has a central carbon with 3 methyl groups. I'm going to draw 2 of them in as just CH3s. The third one, I'm going to draw the protons on the methyl group because it's going to help us to push arrows and see the movements of electrons. So this is another methyl group, but this is one where I'm drawing the H's on it. And then there's a Cl on it. And then I'm going to put a base in here. So the base that I'm going to use is going to be hydroxide, OH minus. And what we should do first is use some of the skills we learned last time to predict elimination reaction products. Find the leaving group, identify the alpha position, and then identify beta positions. So the chlorine is here, so that's the alpha position. The beta positions are all those carbons that are attached to it. And so we've got a beta position here. I'll call it beta. That's a methyl group. We've got another methyl group here, so it's a beta position, but it's not a different beta position. It wouldn't matter if the base plucked an H off this methyl group or that methyl group. or this methyl group because they would all give the same product because it's all the same beta position. So you don't have to worry about what happens if it attacks one or the other methyl group. You get the same alkene product either way. If these beta positions were different, if it was like a methyl group or an ethyl group or a propyl group, then you'd have to think a little harder about that. But so we're just going to pick on this one beta position here, and we're going to draw a reaction. So this mechanism works exactly like we talked about last time, where the base comes by, abstracts a proton off the beta position. The electrons in the carbon-hydrogen bond go to form a carbon-carbon double bond between alpha and beta, and the leaving group leaves with a pair of electrons. And the product that comes out of this is an alkene that's formed between the alpha and the beta position that was deprotonated. So here's the alkene product. Alpha position was here, beta position was there. These were also beta positions that didn't react. The other product that comes out of this, and there's actually a couple. Water is the conjugate acid of the base that we use, so I'll draw H2O here. And then the Cl- leaving group is also a product. Sometimes you'll just see hydroxide or a base listed without a counterion, or you might see like a sodium with a hydroxide. If you saw like just this, then just chloride would be your product. If you saw sodium chloride, for example, Na plus OH minus, then you'd have a sodium cation over here as well. But either way, sometimes you're asked for a balanced equation showing all the products, and sometimes you're just asked to show the alkene product. So just give the question whatever it wants, I guess, is the bottom line. One thing I want to point your attention to is when you see alkyl halide and a molecule like hydroxide, you might be wondering, what about substitution reactions? Do we have to worry about that? We spent a whole chapter talking about substitution. But in this case, this is a strong base. It could also be a strong nucleophile, but this is a tertiary alkyl halide. It's a very poor substrate for an SN2 substitution reaction. So what I'm going to say here is no SN2 reaction due to tertiary alkyl halides. So alkyl halides that are tertiary don't undergo SN2 reactions because they're just too hindered. So we can use this hydroxide as a base, and we don't have to worry about hydroxide acting as a nucleophile. We could also use a bulkier base, and that would work okay too. Like last time, I talked about the tert butoxide bases, which is oxygen attached with a minus charge attached to a tert butyl group. But we don't need it here because this skinny base works just fine. All right, let me tell you a few things about this mechanism. If you're keeping track of like what's going on, it's 3 pairs of electrons that move at once, and it's all over one step. So E2 is concerted. That means one step. All of the bond breaking and forming happens at once. There's no like intermediates that where the reaction stops along the way. It requires a strong base. Because the base is getting involved in the rate determining step. There's only one step, so that's the rate determining step. And 3 pairs of electrons move at once. Another thing about this is the rate of this reaction is equal to a rate constant K times the concentration of the alkyl halide, the Rx component, times the concentration of the base. So that's why it's called E2. The 2 refers to the fact that there's 2 species that are present in the rate determining step. It depends on the concentrations of both of these things. So if you have an E2 reaction and you increase the concentration of the alkyl halide, the reaction will go faster. If you increase the concentration of the base, the reaction will go faster. If you decrease either of these, the rate will decrease. So that's some things about the E2 mechanism that they'll be helpful to know. Let's look at energy level diagram for this process. So I'll sketch a diagram here, a graph. The graph is going to have a y-axis that's going to have energy on it, increasing as you go up. The x-axis is going to be progress of the reaction as a function of time. So this is going to be reaction coordinate. Which is just what stage of the reaction is it at any one point. The reaction is going to start its starting materials or reactants. So I'll draw a line here to represent the energy of the reactant molecules. And that line, I'm going to put the energies of all the reactants. So we've got a tert butyl chloride reactant, and we have a sodium hydroxide reactant. And if you figured out the energies of both of those, they'd sum up to a particular level. Then there's the products, which I'm going to draw over here, and I'm going to draw them right here. And I'm purposely not drawing them lower in energy because a lot of times alkenes aren't actually lower in energy than the alkyl halides they come from, and we'll talk about why that is. But right now then, what I'll do is draw in the product here. So one of the products is the alkene. Another product is a water, what was this? This is a sodium chloride, water molecule, and a sodium chloride. So they have a particular energy, which I'll sketch here. And then there's a transition state where the reaction has to pass over in order to get from reactants to products. So I'll draw this graph like this. And just like we discussed in previous chapters, the height of the hump that the reaction has to go over in order to get from reactants to products is the activation energy. That's E sub A. And that determines the rate of the reaction, how much energy you have to put in to get the reaction to go. And then the difference between reactants and products, actually products minus reactants, is your delta G value. And in this case, delta G, I've drawn it to be very close to 0. So there wouldn't be a strong product or reactant favoring in this particular reaction that I've drawn. But I do want to draw the structure of the transition state here because I think it's important it's going to be important for understanding one of the things that is really critical about E2 rates. So I'm going to draw a picture of the transition state here. So the transition state is going to have bonds partially formed and partially broken. So we're going to have some bonds that are like not participating, but then we're going to have like the bond to the chlorine partially broken. We're going to have a bond to the hydrogen partially broken as the hydroxide base comes by to pluck it off. And then we've got a partially formed double bond here. So this is what it looks like when the 3 pairs of electrons are moving, but they haven't really completed their movements. They're somewhere in the process of moving. A pair of electrons on the base is starting to grab that proton. and make a bond to it. The electrons in the carbon-hydrogen bond, that's for the hydrogen that's getting deprotonated, they're starting to move to form a new carbon-carbon double bond between the two carbons, but it hasn't finished yet. And then the bond between the carbon and the chlorine is starting to break, and the chlorine is starting to go away. It's starting to develop a partial minus charge and leave, but it hasn't completely done that yet. So, so this is the part way done reaction, and it is at a peak in the energy level diagram. But the thing I wanted to point out here is there's double bond character in the transition state here. So this carbon-carbon bond here has got some double bond character. And that's going to be important for understanding why certain types of alkyl halides react faster. So what I want to just say before we leave here is there is some CC bond character in the transition state. And I'm going to point to it with a blue arrow just so you are sure later what I'm talking about right there. All right, and then we're going to talk about some factors that affect E2 rates. Just like we did with SN2, we talked about, what are all the kinds of things that will make an SN2 reaction go faster or slower, or what are things that matter. So this is going to be factors affecting E2 reactions. Think of this as kind of like a table of contents. I'm going to tell you what I'm going to talk about, and then I'm going to talk about it, and then we'll probably summarize too. So the first factor is substitution of the alkyl halide. Just like with SN2, we looked at classified alkyl halides as methyl, primary, secondary, tertiary, and that mattered for SN2. It's going to matter for E2 as well. The second factor is going to be a leaving group. What leaving group is present? The third thing is going to be nature of the base. In SN2, it was the nucleophile. And maybe what I'll do here is instead of nature of the base, I'm going to say strength of the base. In SN2, it was strength of the nucleophile, but in elimination reactions, we're talking about bases. So how good of a base is it? And then factor 4 is going to be solvent. And then later on, we're going to also talk about stereochemistry. Stereochemistry doesn't, well, it can affect the rate of certain reactions, but it's something we're going to kind of talk about next time. So let's go through these with the first one first. So the first one listed here is substitution of the alkyl halide, and that goes like this. So property number 1, substitution of Rx, and here is the way that it works. Tertiary alkyl halides actually give the fastest reactions, fastest E2. Secondaries are slower. Primary alkyl halides give slowest E2. Methyl halides cannot undergo elimination reactions because they don't have a beta carbon. So you can't make a double bond in a carbon-carbon double bond in a molecule that only has one carbon. So you don't have to worry about methyl halides doing any kind of elimination chemistry. So okay, this is a little bit maybe a little bit unclear why this would be if you're thinking SN2 and you're remembering steric strain, steric hindrance was a big problem in SN2. We're not seeing that here. It's the base doesn't really care about or isn't really bothered by steric hindrance, but what matters is this double bond character in the transition state. So I'm going to explain here why this works. So here's the reasons. Bases are not as sensitive to steric hindrance as nucleophiles. Because a nucleophile has to attack a carbon, it has to get past a whole lot of like other carbon blocking groups, whereas protons exist on the outsides of molecules, so they're just inherently easier to grab. So a bulky base, if you've got a bulky molecule that has a lot of negative character, it might be a poor nucleophile, but it could still be a strong base. So steric hindrance, it doesn't really matter as much. That's, I guess, reason number one. And then reason number two is that the E2 transition state has CC double bond character in it. So this transition state up here, the fact that there's double bond character in it means that the more substituted the alkyl halide is, the more R groups it has on it. If you imagine this is a full double bond, for example, then you could classify this and say, well, how many carbon groups are attached to the double bond are going to be attached when it forms? And so from a tertiary alkyl halide, there's more. So the more R groups that are there are able to stabilize this transition state a little bit. They're pushing electron density in to this forming double bond. That tends to make it more stable, and it lowers the activation energy, which means the reaction goes faster. If I was to take one of these two methyl groups away, the reaction energy, transition state energy would go up because it loses this stabilization. If I was to take both of them away, the E sub A would go way higher, and that reaction would be way slower. So it's for E2, it's about this transition state double bond character. And that's the hard one to like kind of remember and wrap your head around for E2. Most of the other stuff, the factors affecting E2 make more intuitive sense. They're easier to sort of grasp just by looking at them. Like leaving group, for example. So 2 is leaving group. Leaving group. Good leaving group is needed. Is needed in E2 because it leaves in the rate determining step, or the rate limiting step. There's only one step in E2, and the leaving group leaves in it. So the leaving group has to be good, otherwise the reaction won't happen. The better the leaving group, the faster the reaction. So better leaving group gives faster E2 reaction. And we know from our discussion in substitution chemistry, iodide is better than bromide, which is better than chloride because of the size of those atoms and the base strength. I minus is a weaker base than Br minus. Br minus is weaker than Cl minus. Then there is 3, which is the strength of the base. Base strength. So base reacts in the rate determining step. And therefore, strong base is needed for E2. And the effect is, if you use a stronger base, you're going to get a stronger or faster E2 mechanism. So stronger base leads to faster E2 reactions. One more note about this is that a lot of times, base strength is really important, but a lot of times people will also use a strong bulky base. And I just wanted to put a note about that. It's common to use a strong bulky base in E2 reactions. Being strong helps make the E2 mechanism faster. Being bulky helps make the SN2 mechanism slower. Which is good if you're trying to do one thing selectively. So a lot of times in chemistry, what we really want to do is we want to have one reaction happen and not anything else. I mean, in my perfect reaction, it would be one where I just get the product I want and no byproducts, really clean. That's not usually ever completely true, but if you pick reactions and set up conditions where you can minimize byproducts, then that really helps. So if you can use any strong base you want in E2, and you're worried about maybe an SN2 reaction happening because it's not a very hindered alkyl halide, then using a strong bulky base helps direct the reaction towards the E2 product, alkene product that you want. Right, and then there's one more factor here for E2, and that's solvent. So factor number 4 is the effect of solvent on E2. E2 reactions are fastest in polar aprotic solvents. It's actually just like SN2. The reason is the solvation of the base. Polar aprotic solvents solvate the base weakly. Which makes it more reactive. it's the same concept that we looked at when we were looking at substitution reactions and strength of nucleophile. The nucleophile in a polar aprotic solvent wasn't solvated very strongly, and that means it could be free to go act as a nucleophile, attack carbons, and do reactions. A similar thing is true of bases in polar aprotic solvents. Is the aprotic solvent doesn't solvate the base very strongly, so the base is pretty free to move around and react with things, and it doesn't carry a big, heavy solvent shell with it wherever it sort of goes to. So the base is more able to act as a base. If you put in a polar protic solvent that solvates the base really strongly, that tends to stabilize it, make it less reactive, and E2 reaction likes a strong base. So that is that concept. There is this thing called Zaitsev's rule. So this is another E2 factor that we're going to talk about, and we've already actually introduced it. So here we're just going to give it a fancy specific name, and we'll look at some examples of the outcome of a reaction and how you can use it to predict what a major product is going to be out of an elimination reaction. So Zaitsev's rule. And there's a couple different ways to spell Zaitsev, and I've seen them a couple of different ways. Zaitsev's. I've also seen a Z-based spelling for it, Zaitsev with a V. It's the same person. And basically what this Zaitsev's rule says is that in substitution reactions, elimination reactions, sorry. Reactions with more than one possible alkene product comma, the most stable alkene will be the major product. So E2 mechanism follows this rule, which is actually kind of nice because if you're looking at an elimination reaction and you're predicting multiple alkene products, all you have to do is figure out which one is the most stable, and that will be your major product. So let's look at an example of this and use this Zaitsev's rule to predict what the major product will be. So here's an alkyl halide that has a couple of different possible products. There's a central carbon atom that has a leaving group, that's a bromide, that's a good leaving group. And then there are a couple of CH3 groups that are attached to that carbon. And there's a ethyl group that's attached to that carbon as well. And let's suppose that this was a reaction that was put in with a base, a strong base, and that's going to give us an E2 reaction. And for my strong base here, I'm going to use hydroxide, OH minus. And this is a tertiary alkyl halide. And that is actually a really good substrate for E2 because remember, the more highly substituted the alkene is, the faster the reaction will go because that's what E2 favors. And we've got an alpha position here. And then we have two identical methyl groups, which I will call beta 1 and here's a beta 1. They're identical because they're both methyl groups. We also have a beta position over here, which is not the same because it's an ethyl group. It's carbon that's part of an ethyl group. So I'll call this beta 2. So the base, when it's approaching this molecule, can bump into two different kinds of beta positions. It could bump into beta 1. So if it were to do that, I'll say beta 1 reacts first. This will be the first thing I look at. I'll have it going to here. So beta 1 reacts. You're going to get out this alkene where we've got a double bond between these two carbons, and this is a disubstituted. If it reacts with the other beta position, and I'll use the purple. If it reacts with beta 2, you're going to get, oh, I'm sorry, this is wrong. Yeah, get rid of that one. This arrow's got to go this way. Goes from here to here, and then the leaving group leaves. When it attacks here, these electrons go there, there, and what comes out of this is this different alkene where the double bond is between the beta 2 carbon and the alpha position. This is a tri-substituted. And so since this is more highly substituted, this would be the major alkene product. This would be the one you'd expect to get more of. This would be minor. It would probably be produced, but less of it. And so this is how that Zaitsev's rule can work to your advantage. It's how it can help you predict what's going to happen. So when we come back next time, we're going to talk about the E1 mechanism and how it works and how it's different from E2, and then how you can tell the difference and what the effect is on the products. We'll also talk about stereochemistry, which determines whether you get a one alkene stereoisomer or another. So I'll see you for that on Friday. And this weekend lab in the Chem 234 lab, we're doing an elimination reaction. So if you're coming to lab tomorrow, elimination chemistry is on the agenda. So we'll look at that. So have a good day.